Geometry Chapter 7 Lesson 2, and we want to look at a very special ratio called the golden ratio. And the golden ratio we can use as a similarity ratio between similar rectangles, and we've been using similar ratios to determine lengths of sides in similar polygons. So you remember that in order to use a similarity ratio to solve for sides in another similar polygon, we write the similarity ratio first, and then we write other ratios that are equal to that one, substituting in a side that we know, and then a side we don't know we use as a variable, and then we solve for the length. But it all begins with that similarity ratio. And in the similar figures up until now, we've been determining the ratio for ourselves, taking a length that's known in one figure and writing it in a ratio with a length that's known in the corresponding side in the other figure, giving us a similarity ratio that we can then use to work with. When we're talking about the golden ratio, it's a ratio that we just need to memorize and know, but it is a similarity ratio that we can use to determine lengths with figures that are golden rectangles. And so this ratio comes from the golden rectangle, and a golden rectangle is a rectangle that if you were to take that rectangle and divide it into a square and then a rectangle left over, the smaller rectangle would be similar to the original. So if you look at this diagram here, if I were to take this rectangle here, and I'm going to try to outline this rectangle for us here so we can kind of see what it is. But if I was to take this rectangle, we're going to have to do something back here. If I was to take this rectangle that you see drawn here, this kind of with the peachish background here, okay, put this here. No, don't do that. So if I were to take this rectangle and divide it into a square and a rectangle, so this side is square and then this side is a rectangle, this rectangle on the right is similar to this original rectangle. Their sides are proportional. And then if I were to take this rectangle now that's on the right here, and I was to divide this into a square, see here, square, this is a square, and then this rectangle, I didn't really do that very well, let me try that again. There we go. This square, and now this smaller rectangle would be similar to this rectangle and similar to the original. And I can keep doing this over and over again and keep getting these golden rectangles, or these rectangles that are similar to each other, by taking the rectangle and dividing it into a square and a rectangle. So a golden rectangle is a rectangle where you can do this, where you can divide it in a square and a rectangle and create a rectangle that's still similar to the original. Alright, so that's what a golden rectangle is, and the ratio of the sides, whoops, everything disappeared, don't want to do that. The ratio of the sides is always the same. And so if I take this golden rectangle and I made this side 1, then the other side, this longer side, would be 1.618. So the golden ratio is the ratio 1, which represents the shorter side, to 1.618. And every other rectangle that I draw or that I create by making this square and rectangle will be, those sides will be in the exact same ratio. So with the golden ratio, we're actually comparing the lengths of two sides in the same rectangle. But the property is that that ratio is the same for all golden rectangles. So rather than writing a ratio using the side in one and the side in the other, we're actually using the sides in the same rectangle to write our ratio, because all of the other rectangles that have this property will have the same ratio. And then I can go ahead and write another ratio, making sure that I keep the smaller side lined up with the 1 and the larger side lined up with the 1.618, and then I can write my proportion. So anytime you see the phrase golden rectangle or golden ratio, you want to think of this ratio, and this is something I would expect you to memorize. So let me show you how you can apply that to a problem. So here we have a switch plate for a standard wall switch. So the plate that goes over the switch in the wall has the shape of a golden rectangle. So that wall switch plate is in the shape of a golden rectangle. So it's a golden rectangle. So the longer side of the switch is about 114, what is the length of the shorter side? Now, in order to solve for x, I need a ratio, or I need a proportion. So remember, when we worked before, we need a similarity ratio to begin with. Well, because I know it's a golden rectangle, I know what the ratio of these sides should be. 1 to 1.618, so I can begin with this ratio. Then I simply write another ratio using a value that I know and a value that I don't know, and then I can solve the proportion. So this 1 represents the shorter side in all golden rectangles. So in this switch plate, the shorter side is x, and the longer side is 114. So as long as I line those sides up with the golden ratio, I simply have a proportion now where I can use the product of the extremes is equal to the product of the means. And then I simply solve this. So this is going to be 114 divided by 1.618 millimeters will be the length of the switch. Now, because this is a measurement, we don't want to leave it like this. We will actually calculate this because it is a standard measurement, so we don't want to leave an improper fraction. So when I divide that out, I get an answer of about 70 millimeters. So the smaller side of this switch plate will be about 70 millimeters. So we're not doing anything different here with the similarity ratio or the golden ratio. It's just the fact that we already know what the ratio is, so we have to begin with a similarity ratio. So we know what it is by the term golden rectangle. As soon as we see golden rectangle, we should think golden ratio. That's going to be the similarity ratio that we begin with. All right, so that will wrap up Chapter 7, Lesson 2.